So I would like to welcome everyone to our product showcase presentation, Thermally Broken Shelf Angles, organized by New York Pacifiers and presented by FERO. I would like to thank FERO for your support as a sponsor during the last years. And FERO provides innovative products developed through decades of research, development, and engineering expertise. It is my pleasure to introduce Adam Kimble, who is the sales director at FERO, and Michael Ross, senior technical advisor, moderating today's Q&A session. So Adam, please take it away.
Yeah, thank you everyone for joining us today. We're excited to present strategies and components to create energy efficient masonry wall assemblies. As mentioned, I'm Michael Ross, and I'm one of the senior technical advisors here at FERO, and I'm pleased to be joining Adam for the presentation, and I'll be able to moderate any questions that you have. Just type them into the chat feature, and we'll be able to answer them throughout the presentation. Then we'll also hold a question and answer period at the end. A little bit about FERO really quickly. We were 1980 engineers with a focus on innovative facade performance of all assemblies, with the view that demand for energy efficient facades requires continual innovation. Our products were designed to meet energy and thermal performance standards decades before those thermal performance standards became critical in building design. If we run out of time for any questions, someone from our team will reach out via email with the information that you've requested. Otherwise, please feel free to put any questions in the chat function and I'll answer throughout the presentation. Thanks again for taking the time to join us, and Adam can take it from here.
Hi, everybody. Thank you again. So I see that we currently are trending up to 35, 36 participants. Thank you for participating today. My name again is Adam Kimble. I'm a structural engineer by training, and I've had the opportunity to work with FERO for 3 years now. And I live in New Orleans, and so we had this little storm come through called Hurricane Ida. So if you hear any grinding or just any kind of machinery going on in the background, that's people fixing our house. So my apologies for any extra noise that you may hear in the background. Hopefully it's not too distracting. But yeah, today we'll talk about energy efficient wall assemblies and considerations in masonry buildings. As Michael, my colleague, mentioned, FERO started off in 1985 as a masonry accessory manufacturer, and we've grown into other facade things. So I always talk to, when we're talking to our customers, that we're kind of in the niche of an engineering company that provides facade connection. So today we're going to talk about our products, mostly about our offset shelf angle system. So this is the part where I say that this presentation is an AIA presentation in which we'll talk about generic topics, and I won't be material based. And so what we're talking about today is you'll hear common terms such as offset shelf angles. What we're really talking about is FERO'S thermal brackets. That's kind of the trade name or the proprietary name that we go by. And so that's the things that we'll talk about today. But after the presentation, we'll be glad to give you AIA credits based upon your presentation today. So as mentioned, FERO manufactures some of the things that we manufacture are offset shelf angles, thermal masonry ties, also breakaway fire release connectors, which is a product that continues to grow both in school settings and also warehouse construction. And so we can also give you a small presentation about that if you're interested, and that's something that you would be looking for, and also custom structural connections for any other facades. So today we'll talk about our current challenge, meeting the energy code. Last May, during the midst of the pandemic, New York City came to their new energy code where it says you actually have to calculate thermal bridging at locations such as balconies, parapets, and shelf angles. And so the current challenging is designing an efficient masonry wall system to meet the demands of expanding energy codes and guidelines. So, there's the benchmark as far as the energy code, and then there's, the carrots such as the zone green incentives that you have if you can meet those goals in New York City. What we have here is brick is an inherently energy efficient veneer. So if you look at primitive buildings, they were generally made out of clay or some type of mud, which is a kind of a base of clay. And it has a great thermal flywheel effect. So it gets warm during the day, but keeps it cool inside. And it transfers that heat from that it's storing from the day and transferring at night. So it's actually a quite efficient veneer in how it transmits its heat. Designers are increasing their insulation thicknesses as well. So, you know, we're all now become accustomed to having our continuous insulation outboard of our structure. But larger wall cavities require larger shelf angles to support the brick veneer. And so that's what we're talking about here in this location. And so this is the things that we want to focus on today is how to make those larger shelf angles that create a number of issues and challenges for designers and installers. So the three things that we'll talk about in the presentation at identifying the problems is thermal bridging. So what we have here, there we go. So thermal bridging. So we have an angle here that is a linear thermal bridge. And you'll hear me talk about this throughout the presentation. And thermal bridging is a term that is we hear more and more, but it's a very simple factor. Thermal bridging is the surface area and the mass of the material. And so what we have here is a long linear thermal bridge that goes around the whole perimeter. And then we have our mass. And so when we think about thermally conductive materials as the structural elements that we generally use, we have wood, which has a relatively low thermal conductance compared to concrete, which has a moderate thermal conductance, but by far and large, steel has the highest thermal conductance. So based on those two factors in the equation of thermal bridging, we have a very large thermal bridge here. And so as this angle gets thicker, it creates a larger thermal bridge. And so that's the first thing. The second one is the difficult to install. So as more insulation here in the cavity, this angle gets larger, which it turns into ultimately is getting heavier. And so it's a conventional shelf angles cannot be adjusted easily as well. So imagine you have a cast in place slab, then you have to anchor these in. We commonly see people use embeds, but what if the embed is not placed properly or it's not in the correct location? They have to drill a hole through this really large thick angle. And if they're drilling holes through the slab, they might hit stirrups or rebar as they're drilling through, all the while trying to lift this very heavy angle. And then most importantly, it's very expensive. As we all know, anything in building materials from caulk to steel has gotten extremely expensive. So these are the things that we want to address throughout our presentation and how to resolve these three common problems. So first, thermal bridging. So here we have the ugly, bad, and the good. This comes from a counterpart, which is a envelope consulting company called RDH. They put this detail together to kind of identify why are these things becoming such an important detail to consider. And so in the buildings that did not have continuous insulation, you would have a stud wall construction, you would have a 4x4 by quarter-inch angle mounted to the slab edge. And so while there's a small thermal bridge here happening, generally the biggest thermal bridges that were happening at this point in time when we just had batten insulation in the walls is all the studs here. And so while there is this linear thermal bridge here, there was a lot more linear transmittance of energy loss happening here at the stud wall assembly. And then there's the bad. So we said, okay, yeah, continuous insulation is actually the proper place to put it, So we now put our continuous insulation outboard of our walls to address the thermal bridging at the studs. But then we had to accommodate the depth of this cavity happening. So this one just had an inch air cavity. Now we have 3 inches of insulation, inch air cavity, and then the brick. And so now from a 4x4 to a quarter-inch angle, we go to a 4x7 by 3/8 or half-inch angle. So while we solved the studs thermal bridging, we've increased now at this point the thermal bridging at this angle. So how do we solve that? Ultimately, what we want to do is we want to maintain our continuous insulation, but rather than having a linear thermal bridge with a large angle, we want to make this a punctual thermal bridge only and use a lighter angle like we did here, which is a 4x4 by quarter-inch angle. So reducing the mass and also reducing the surface area. So this is the fundamentals, is that we're reducing the mass and the surface area. So here's a therm model. So here's the assembly that we can see here on the left, and then the therm model as it was running, and to demonstrate the energy losses in the model itself. So here at the we have our brick veneer, we have our insulation plane and our control layers, and then we have a CMU stud backup wall and our floor slab. So as you can see, we have a masonry tie here at the top. This is a great benchmark to point out because this is the location where you can see that the thermal transmittance is finding its delta at the right location, and that's inside of the insulation layer. We can also see that's happening here with our through-wall flashing, but then we have a problem here where we can see that actually the angle itself is finding its delta of the heating and cooling here in the structure itself. And so this is the effects of where you find cold feet, you find moisture and condensation building up the wall, depending upon the humidity index and the temperature. So these are the things that we want to resolve. And one thing to point out, depending upon where you're located and how you're designing your buildings, being at a temperate location or not, energy costs are roughly the same in colder climates, heating a building as it is cooling a building in warmer climates. So thermal bridging is not only a phenomenon in colder climates, it's also a phenomenon in warmer climates. We generally just don't have the feel for it because when our feet are stepping on cold floors in the winter, we can really identify that rather than stepping on warm floors during the summer. So it's just more of a feeling effect. So that's a model, but it'd be interesting to see actually how this is happening in the real world. So here's the therm photo. And so the benchmarks that I always like to point out is here at the top where the parapet's happening, where it's probably poorly insulated. And then we have some really poor punch window conditions here. So in a therm photo, the whitest is the hottest. And so we can see really there's quite a significant amount of energy loss here at the parapets and the windows. But there's also a significant amount of energy loss here at the shelf angles. And so, keep in mind at all this brick veneer here at 16 by 24 inches, there's a masonry tie that's made out of carbon steel generally as well. You can get those out of stainless, but generally they're being specified as carbon. And while there's quite a lot of surface area where these masonry ties are located, the mass isn't there. So you think about the mass of a masonry tie is generally something like 9 gauge material. And so it's relatively thin, whereas we have an angle here that at minimum would generally, with 3 inches of insulation, is going to be a 4 by 7 by 3/8. And so we have a really long linear thermal bridge and quite a significant amount of mass here. So whereas you can see how so this is the heat being emitted from the building, whereas you can see how cold, for instance, this is the stairwell. So I have not a well-insulated area. And so you can see the heat loss happening here, the windows and our slab edges. Moving on to installation challenges. And so these are the things that, when you're getting costs from your these costing exercises, and when a mason's bidding it out saying, okay, well, this is my price, these are some of the things that he's having to factor in on how to put your assembly up when you're specifying the things on the building. So when you're specifying a 4 by 7 by 3/8 or 1/2 inch angle, he's also got to consider how does he actually get that up on the wall. So when we look at this, we always point out to start here as the base, a 4 by 4 by 1/4 inch angle is 6 pounds per linear foot. And this is usually used commonly in a loose lintel condition. So masons generally buy these at 10-foot sections. And so that would be a 60-pound 10-foot section. Then we get to a 4 by 7 by 3/8. That would be 13 pounds per linear foot. So now we've more than doubled from a 4 by 4 by 1/4. And so it's 130 pounds per 10-foot section. But we've seen this 8 by 8 by 1/2 inch. So we've gone to almost 4 times, over 4 times as heavy. And we've actually even seen these bent plates as well that are 8 by 8 by 1 inch thick. So these are 9 times more heavier than your common 4 by 4 by 1/4 inch angle. And so think about this when you're specifying these things. How does a mason actually get this up? How is he hoisting this up? Is it just purely brute force? All these things are all fundamentally going to slow down the construction process of him laying bricks. And so this is going to end up creating extra costs just because his labor costs are his biggest money expenditure on a job site. And then we go to increased costs. So we'll definitely talk about one-to-one comparisons, but some of the things that you may not consider just beyond the pure cost of the angle itself, but also the things that you would consider as far as the ancillary things. So you think about the cost of welding or drilling holes in the shelf angle. Again, drilling through a 1/2-inch angle or having it punched and then having to try to connect that while lifting up a 230-pound angle at these locations is pretty heavy. And how does that happen? And if this hole is not lining up with the embed, they have to drill through this concrete, and then they have to hopefully, fingers crossed, they're not hitting any rebar. Generally, anchors are much larger. The bigger the angle, it requires a bigger anchor or tighter spacing, which is also increasing the cost. And the size and weight of angles results into additional costs of labor and equipment to hoist it. So now they've got to allocate time for the cranes or have some kind of hoisting mechanism that's attached to their scaffolding. And then lastly, larger shelf angle sizes are more expensive and material to source. More importantly these days, supply chain issues are real issues these days. And so when you get into these larger angles, they're having to bend it from flat plate. And all these things are finding more and more scarcity out there, so which is lending to bigger costs. And then lastly, lip brick are required. So you think if this angle is 3/8 of an inch thick, that's the same thickness as your brick joint. So that's why you would have a lip brick to hide this large angle. If it's any larger than 3/8 of an inch, it's bigger than your lip joint. It's bigger than your mortar joint, so you're having to hide these in your lip bricks there. And a lip brick is $4 to $5 per brick itself. So do the calculation on the linear footage, and you can figure out how much as a premium that would be. So as we move forward, we'll talk a bit about the solutions. One of the things that I always like to point out is with engineered systems like this, you want to have a company that has a background, and not only a background of manufacturing things, but also a background of testing and data, and can point to you how they've come to the results of how to space these things like this properly, how it's going to tie back to the structure correctly, et cetera. And so, for instance, here at FERO, we've been doing this since 1985. There's over 40 years of experience. So the founder of our company was the head of the National Research Committee for Masonry in Canada, and was a lot of codes that were developed by himself. And so myself and my colleagues included, most of us are engineers. And so this is really helping you identify how to use these things appropriately. One of the things that we do and advocate for any of your projects that this be part of the delegated design process, where you would get the spacing from the manufacturer, and it would be identified on what's the proper products that should be used, the spacing, the depth of the cavity, the height of the brackets themselves. And so these are some of the things that we want to point out that is important. So yeah, and so if you've studied masonry in college or anything, you may have actually even studied with one of our founders' books, Dr. Mike Hatzonakoulis, that actually created the textbook for masonry design. So here, as we move from the status quo to how we would like to see it happen. So rather than the insulation being on the angle and the angle being anchored to the face of the slab, what we're going to do here is now we're just going to have brackets at these locations, or offset shelf angles brackets. And these are going to be generally spaced 4 foot on center, sometimes more, sometimes less. It's really the two factors that determine the spacing is the depth of the cavity and the height of the brick. And so in this case, we have all of our insulation behind the angle. And so the only things that are creating a thermal bridge is the punctual locations where the brackets are connecting back to the slab. The brackets themselves are only 3/16 of an inch thick steel. And also to make this further thermally improved, we punch out all the holes and taking out any superfluous steel. So, and so then we're using a 4x4 by 1/4 inch angle here. So again, less mass here on the total system, less weight as well. And so this is how we would ultimately provide a solution here for this. So we get on to the thermal performance. So we start here at the, what is our benchmark? What's our nominal wall value or clear wall assembly. And so here in this example, we use 4 inches of mineral wool insulation, which provides us an R value of 16.8. And then we look at using a conventional angle of 4x7 by a 1/2 inch angle here, and that gives us an effective R value of 10.8. Whereas compared with using fast brackets here, we have an effective R value of 16.7. So when building up this assembly, we're having from the benchmark of a conventional angle to the fast bracket, we're improving that by 83%. And we're only reducing the effective nominal R value to the effective R value by 0.1 ultimately. So here's an interesting a study that was done by the Colorado Masonry Systems Design Guide. And what they came to the conclusion on, always like to point out, is that the second paragraph. It says for steel stud and concrete masonry backup walls structures, an additional 2 inches of an exterior insulation or more may be needed to offset the thermal losses created with using continuous insulation shelf angles as opposed to an offset shelf angle. So, so that's really the decision maker. Again, factoring the cost of what you're doing in your building. So when you're trying to go to the DOB in New York and say, hey, we're trying to submit our thermal calculations, and you're having to now say, hey, what is the thermal bridge at the shelf angle? These things could ultimately impact if you're having to add insulation or not, just simply because of detailing either a conventional shelf angle or something that's more of an offset shelf angle system. So these are real costs that we have to consider and the impacts about detailing our shelf angle systems appropriately. So simplified installation. So as we think about the conventional shelf angle, it's a linear item, it's rigid, it can't be adjusted, and they have to make sure that they're hitting the right spots with that angle that has embeds, or they're going to drill into it. But that angle doesn't consider any out of tolerance. So if there's the slab is out of being plumb, or if it's not level, you have to start re-drilling holes to make sure that that angle itself is flat and plumb. So whereas with offset shelf angle systems here, you have a 1 3/4 inch slots that goes up and down, and this goes left to right, right to left as a friction connection to make sure that it's effectively fighting against each other to lock itself in. But this will give you the adjustability up and down in the case that there's some highs, peaks and valleys in the slab. And then if it's out of plumb, you can use shims. Generally, we can shim up to 1 inch. And so this is how you would get out those areas of out of tolerance. In addition to that, offset shelf angles such as this can be manufactured as a standard at every 1/2 inch increment. So we start at 1, 1.5, 2, 2.5, 3, etc. And then if there's a specific need to make these exact, that can be manufactured to that specification as well. So this is how you would provide the adjustability in the case that there's a lot of in and out of tolerances. Also, it can be made to any depth or any height. So depending upon your insulation or if you have drop-down windows, you can make these to any depth. I've seen these as deep as 18 inches, and we've made these as deep as 5 foot deep. So imagine if you have a mezzanine floor on a mid to high rise building and you've got 20-foot ceilings, but your window wall is only at 15 feet, you have a 5-foot drop, and that would be how you would solve that solution. So here's a great example of how you can resolve out of tolerance concrete. And so as you can see here, that the slab has a huge belly that happens coming from a corner to the other side of the building. So here we have a nice straight angle that's not going to bend. So we have this bracket here that is an inch depth. Then it grows within 2-3 feet to 2 inches of depth. Less than 2 feet, 4 inches of depth. So it grows 2 inches over 2 feet. And then from another 18 inches or so, it goes another 2 inches. So over a 6 to 8 foot span, it's grown 5 inches out of tolerance. This is something that would be virtually impossible to do with conventional angle. I'm actually not even clear how that would be done other than using a lot of bent plate and a lot of welding and grinding and things like that. So These are the things that just consider not only the thermal efficiency and the installation practices, but also the just the construction tolerances as well. So here's a bit of a presentation that we'll go ahead and play, and I'll let this take over here, how it's installed. So that just gives you more of a dynamic feel of what brackets look like would be on installation. What's the assembly of those with your through-wall flashing and your membrane, so your control layers, and coordination with your masonry ties there. So as we move on, we'll transition to some of the details that you may be wondering, how do I detail this properly? So again, we have our installation behind the angle with the offset shelf angles here. You would have your through wall flashing coming over the fast bracket and then down onto the angle and then coming to your drip edge flashing. And then you would have your membrane following that with your mortar collection material. And so this is our standard bracket. And so here you can see that this has a foot that's supporting the bottom of the angle. And so you would use these commonly in masonry to masonry transitions or skipping windows when the windows aren't either too wide or the brick above that window is not too high. In conditions where the brick is too high above a window or the span of the window is too wide, we would then transition to a lintel bracket. And so you can see here now that foot is no longer supporting the bottom horizontal foot of the angle, but now it's supporting it at the vertical leg of the angle here to give you that flush bottom at these transitions. And so here you can see that these are extended brackets because the brick is coming down further than the bottom of the slab itself. So in conditions that are larger than 25 inches, we need to introduce further lateral bracing. And we think this is a pretty elegant solution to the alternative kicker system. Whereas if you had kickers, there would be some kind of metal system here that would go on a 45-degree angle where you have to consider how to hide this, either being a fur down or drop ceilings. Whereas this, you have your fast bracket that's here outbound of all your control layers, as you can see here. Then there's this plate that is fastened in between your dense glass or gypsum board. And then you have this back fast brace here, which is actually inside the stud wall of the cavity. So there's no anchoring. This is just a bolt with a flat washer on the top that is tightened. And this is to provide the lateral bracing, but it's also to make sure that this bracket itself is maintaining its plumbness along the drop itself, because even if the slab had a 16th or an 1/8 inch out of tolerance where it kicks back in, over a longer span of this bracket, you would have tell for it to happen. And so this provides that adjustability to push that back appropriately to provide the required plumbness for the brick to be supported. So not only is it for bricks, but it's also for transitions of masonry conditions. So here we have an inverted bracket. So you could have some kind of fiber cement board or EFIS or metal panels below or louvers. And then you would have masonry above. And this is an inverted bracket. So no longer is there feet that's in supporting the system, but there's a pocket that takes the vertical leg here and turns the angle 180 degrees where you're placing your brick on the bottom side of the angle effectively. So you're still maintaining all your insulation layers here between at the facade, and at the face of the structure, mortar collection material here as well, and for water egress. So, through the presentation, you see most of the details are centered around in situ concrete. And so we also have other conditions where you say, well, how do I connect it to such as? And so there's conditions where you can connect it to a steel backup wall, either being a flat plate at the stud where it's anchoring, or you could put a flat plate across the whole assembly of the cold form studs. Then there's W sections where you would have an angle here bolted to the top of the flange and connecting it to the bracket itself. Going into tube sections. So this could either be a through bolt connection where you go through the bolt and you have a washer and a nut on the backside, or you can use proprietary expansion steel anchors such as LINTEL anchors as well as an alternative. And then you have thin slabs. So this condition is we see commonly used for pan deck systems or composite decks, or even alternatively hollow core deck systems as well. One of the ones that you don't see in here, but is pretty common as well, especially in the New York market for low-income housing, is block and plank systems. So rather than anchoring onto a hollow core deck, you can also alternatively anchor offset shelf angles into a CMU block as well, where you would just either through bolt it or use a proprietary anchor from Hilti or Powers, depending upon the loading conditions that are necessary. So some other things that might be interesting for architectural effects. So here we have a double bracket, which is a bracket system that could support corbelling conditions. And so this bracket can be could step out to support as your brick sweeps. Fast flex system. So this is an angle that we can manufacture that's augmented and bent to match the profile of that radius in coordination with the fast brackets, which is another variation of fast bracket, where this clip holds back the angle as the angle is being supported there. Custom angle supports. So we've done a couple of jobs in New York with this condition. We've done this condition. This is a specific condition in New York. It's at 2505 Broadway, where the piers, the brick, so they meet their insulation requirements, but the piers had a brick profile and they wanted that brick profile to the angle to match that brick profile. So we manufactured this custom angle in addition to with the fast brackets in this. Also concealed lintel clips. We do this quite a lot. The next project you'll likely see this on is the Broome Street project. And there's two buildings there. It's a Suffolk and Norfolk building. One of these being a mid or low high rise, I guess, or mid rise. And so rather than exposing the bottom part of the angle, in addition, we can also give you a more aesthetic reveal where the brick comes to the underside here, and masons either have the choice of using a one clip solution, which is done on-site, or a two-piece solution, which is done off-site, where they thread the brick onto the rods, they bring it on-site with this tab coming out, and they bolt this on together at the end. Okay, so we're at 11:36 here. And this is the part of the presentation where I think maybe you all have been able to participate in, and you're like, this seems like an interesting product, but I'm interested in how much this costs. Then one of your fellow colleagues, or maybe yourself, is the brave soul that says, well, how much is this? And the person that does the presentation turns to a bit of a dancing analogy of sorts to divert that question to ROI or life cycle costs and things like that. And at the end of the day, many of our customers that we work with are concerned about green elements of our buildings, but most importantly, the things that they're concerned about that's green is the things that's in their pocket. And obviously that, that has to be considered, because they have a building that they have to build that they are looking to make money on. And so they have to find a balance of meeting the energy or green initiatives that they're looking for, but also meeting the green initiatives for their company to maintain profitability. So the conventional shelf angle. So we have going back to where we were previously with 4 inches of mineral wool insulation, an inch airspace, and a 4-inch brick that has an R value of 10.8. Using a 4x4 by 7 by half-inch angle. Probably a bit more expensive these days, but on average, it's been $21.25 per linear foot. And some people think it's counterintuitive to consider how can I add a product and save money? And where we go with is it's all fundamentally that we're using less thick material and using it less often. So again, we have a offset shelf angle here that's 3/16 of an inch. We have a 4x4 by 1/4 inch angle here. So that has an R value of 16.7. And so this bracket here is roughly $24 at 4-foot spacing, which gives us $6 a linear foot. And the shelf angle itself is $7.25. So we're at $13 compared to $21 per linear foot. And so that's a $8 per linear foot savings on any project that you're working on current or in past. Think about how many linear feet of that floor slab there was times how many floors, and then you can take $8 and consider how much savings that you would have had. Also, the numbers actually start becoming even more impressive when you think about things that have to drop down to get to the window head. And so here in this condition, we use a built-up system to compare. So here we have a pour stop. We have a tube section here with a knife plate and then the angle. So here we have the HSS, the knife plate, the shelf angle, and the slab, the pour stop here. And so that with the Nelson studs as the embeds, that comes to $95 a linear foot. By the way, all of this is a welded connection. So this is adding somebody else to the sequencing. So imagine somebody's pouring the concrete, then you have a steel erector out there putting this welded assembly out together, and then you have a mason that's installing his brick. Whereas this, we still have the concrete form worker, but these are all bolted connections. And so there's no welding that's necessary. So there's no steel erectors necessary. And so we say form worker, mason, so he can control his own scheduling. So he's going to install these brackets, 4 foot on center with the punched angle. That's a 4x4 by 1/4 inch. So we're at $63 per linear foot savings. Again, take that by how many linear feet times how many floors, and you can multiply by $65 per linear foot and identify the savings that you could have. So, not only is it material cost, but it's also the things that you have to consider from the installation and the ancillary things that you have to consider when using larger conventional shelf angles. So shelf angle installation reported by installers to be twice as fast with offset shelf angle thermal brackets compared to shelf angles. We actually have many masons in New York that they've tried on the first time with fast brackets, and after that they switch any project that they take on as their scope of work from conventional shelf angle to now offset shelf angles. So this is actually their preferred route to installation, and they're doing it for their own savings, not because they're focused equally on energy savings. This is purely because they know that they can get it installed much quicker. Also consider for conventional shelf angles, the labor for hoisting and installing shelf angles. So you think a bracket itself is 3 pounds. A standard shelf angle, the standard bracket. So here's the standard bracket. And this bracket is, 3 pounds. So much lighter than individually. So they're going to install each one of these individually and then put that 4x4 by 1/4 inch angle. So, and they're adjusting all these individually, making sure they're plumb and level. And once it's all getting installed, so there's no need for any large mechanical equipment to be to erect these compared to the conventional angle itself. Also, the potential consideration of removing lip brick. This helps out with your drip edge flashing, and rather than having a tail down and then out, you can just use standard drip flashing that has a 45-degree tail. And you also don't have to buy these lip bricks that are quite expensive comparatively. A lower cost of shelf angles, so thermal brackets can span the cavity, so smaller shelf angles can be used. So this is also, think about the freight costs, so lighter angle, lower freight costs, and it can be sourced locally, whereas these larger angles, anything beyond 4x7 by 1/4 inch, ½ inch material is actually bent plate, where they take a flat plate and bend it 90 degrees. And then also there's no welding or drilling holes in the shelf angle required. So this is another savings just from the installation and coordination schedule. So as we're wrapping up the presentation, we always like to just take a little bit of time to talk about the comparisons, because there's information that's out there that I think is always important to understand the key differences, and just to point out when considering alternatives. So there's ad hoc solutions or on-site solutions that are out there. And so what we see here is a tube section welded to an angle. And so this is going to require a steel erector to install this. It's quite expensive comparatively. There's no adjustability into this and at the site. They're going to be welding this together and spray galvanizing it, whereas all the brackets, angle, et cetera, is all hot dip galvanized. And so, and then there's the thermal performance is going to be significantly less. And also this is something that your structural engineer is going to have to design. Whereas with offset shelf angles, the manufacturer would be doing the delegated design work, signing and sealing the drawings. There's manufactured knife plate solutions as well. And so some of the key difference here is that the angle comes welded to the knife plate in this condition. And so this is all going to have to be shipped. You have to buy the angle with the knife plate. You also have to buy the anchor channel. So all three of these components are required to come from the manufacturer, which could be significantly further away. And the question is, why would you want to buy angle from somewhere as far away when you can buy it closer to the job site and reduce your carbon emissions and costs, et cetera. It also requires the components to be bought together. More complex, leading to increased labor, and often requires the anchor channels or wedge inserts to be bought. So also considerably more expensive. So as you can see here, in this condition, whereas the standard bracket is bought from the manufacturer, the angle is bought locally, and the anchors can be bought to whatever you want. It can be an embed, it can be post-installed, whatever the preference is. Whereas this, you're having to buy all the components at once. We get time to people asking about these thermal pads. And some of the things that people are not aware of is that generally these pads are more expensive per unit. The thickness of the thermal pad is commonly limited to 1/2 inch or 3/4. And if it's any thicker, you have to add more bolts to this to reduce the bending. So then there's no reduction to the shelf angle size. So if you think about this, you have the pad, but you still have this really large angle here. And so again, what is our two components to determine thermal bridging is the mass and the surface area. So you have a 1/4 or 3/4 inch pad that doesn't create a lot of insulation behind the angle, but still have a relatively large angle that's creating a lot of thermal conductivity. And then your insulation is on the angle. So no cost savings in the angle, no insulation behind the angle, and a lot of more engineering considerations. So lower load capacities requires tighter spacing, so based upon the bolts. Requires also longer bolts, which is a key concern for structural engineers because of the eccentricity that's being induced on that bolt. And then lastly, what is the fire considerations for this combustible material here? So people ask us, what's the cost comparisons, and can you use pads behind brackets? And so we always want to point these things out. So here we have a bracket here that's at $24 per bracket, gives us a $6 a linear foot cost. Coupled with the angle, that's at $7.25, and an anchor bolt. And this, just to use apples to apples, which spaced at every 4 feet, is $1.68. Compared to a composite pad, so the composite pads are $12 each, so $6, that's not quite right. But the 6x6x5/16 angle is $21. So it gets us to, oh yeah, that is right, actually. So, and then the Hilti bolt is $3.38, which gives us a total cost of $30.38, which is double the cost of using an offset shelf angle system. And then people ask us, well, can we actually add a pad behind this to get the offset shelf angle system to improve thermally even better? And so here we have a shelf angle, a clear wall assembly that's at 16.8, and using a conventional angle, it brings our effective R value to 10.8. Putting a thermal pad behind that conventional angle only improves it to 12.4. Then we look at fast brackets, it gives us to 16.7. And then at that point in time, adding a pad gets you 0.3% point units better. So from 83 to 86%. So it's a 3% improvement. But keep in mind, doing this if you say, oh, I really want that 3 percentage points improvement, the spacing ultimately goes down as well. So the price is also getting jacked up even further in this. So now it's a combination of both, and it's going to go to this side. So what I always say is that in this kind of scenario, we really don't see the juice that's worth the squeeze in that consideration, especially when you're pretty close to the nominal R value of your insulation already anyways. So we've done over 1,700 projects in North America at this point, and we do them from as far south as Texas and all the way to the Nunavut territories, all the way from the west to the east coast, and we do them from academia to high-rise towers. And so people ask, well, when's the appropriate time to use an offset shelf angle system? And I would say if anytime the building is above 2 stories, that's when you would use an offset shelf angle system. Shelf angles are designed as a horizontal control joints for your masonry, just like as you would have vertical control joints for your masonry. And so, which gives you, you can basically have those control joints up to 20 feet. And so that's the beginning. Obviously, there's more engineering considerations to determine where that shelf angle should be located. But generally, above 20 feet is when you're going to start looking at an offset shelf angle system. So here's some of the projects in New York. And so you can see that they vary in height and scale and dimensions. And so we are a proud sponsor of the new Passive House, and they do a great job promoting Passive House buildings and the philosophy behind the practices to do such. And I'd like to, so you can see here, the last 3 Passive House towers that have been built in New York have fast brackets on them. And so I'd like to point out that our products are Passive House certified. So if you go to passivehouse.de and you look in the certifications at the wall assemblies, you will see fast brackets there for temperate climates. Those were done with stainless steel to meet the rigid requirements of it. But in the 3 Passive House projects that we've done in New York, we actually were able to achieve the complete Passive House designation with just carbon steel fast brackets. So both our ties and our brackets are Passive House certified, which is, we're the only North American manufacturer that can make that claim here. So if you're looking to specify a Passive House certified product, at this point in time, we're the only North American manufacturer that can actually make that claim. So as you can see, again, here's projects across Canada. And as we're wrapping up shortly here, I'd like to leave a little bit of time to see that there are some questions, some things in the chat. So we'll talk quickly about our masonry ties. So masonry ties, the things that you have to consider is structural performance, cost, fire resistance, performance at low temperatures, and the durability as well. One thing that I didn't share in the offset shelf angle system presentation is that at FERO, all of our products are vertically, from engineering, vertically integrated all the way to manufacturing. So we do all the design, specifications, delegated, sign and seal on the drawings, all the way to manufacturing, where we cut, bend, and even hot dip galvanize our products, which is also rare in the masonry accessory manufacturing industry. Quick review of how we actually were the only manufacturer to reach Passive House designation for our masonry ties as well. So here you have a typical galvanized steel masonry tie, which is negative 24% reduction to your nominal R value. Then you have composite ties that are self-penetrating ties that reduce it to have a 7% reduction of your nominal R value. But using our thermal stainless steel wrap ties, where we punch out again all the superfluous steel, the steel is relatively thin, and we can generally space these out further compared to something like this. We have roughly a 4% reduction of R value. So again, if you're looking to design a Passive House building and you're looking for a Passive House specified tie, this would be the one that you would be looking for. So just to kind of wrap up, there's different assemblies for different applications, be it the types. One reason that we can space our ties out further is the rigidity of the tie, but also how we make our ties embed into the brick. Most manufacturers turn theirs in, whereas we turn ours into a V. And so we're increasing the surface area and the bonding strength of that brick and the mortar itself. And so also we make these things called shear connectors. So if you're familiar with precast, where they use the inner and outer whites of precast to make a composite wall, you can also do that with masonry as well, where you're using the either CMU block or studs to create a masonry white wall there. So potentially reducing your wall thickness as well. So from, if you had a 12, you can go down to a 10. And if you had 10, you could possibly go down to 8, etc., by just creating composite wall systems here. So more occupiable space. So that's the end of the presentation. And now I open it to Michael to address any questions that he wasn't able to address clearly in the chat.
Great, thank you, Adam. Yeah, we have 2 questions that came in right at the end. The first one is from Jane Sanders. What's the expected life of the carbon steel brackets compared to stainless steel brackets?
Generally, they're the same. I don't know if there's been any exact studies on that. Michael, I'll leave it to you if you have any insight on this. But generally, we, aside from the thermal performance, so stainless steel is 70% less thermally conductive than carbon steel. So if you're looking for thermal performance, that would be the reason why we use stainless. Alternatively, the only time we generally have brackets made out of stainless or even ties made out of stainless is to some kind of condition due to closeness, being an approximation to the sea. So salt spray or things like this, or if there's some kind of chlorides in the air, for instance, like a pool, an enclosed pool is when you would want to use stainless. Michael, any other thoughts on life cycle of carbon versus, and when we say carbon, please keep in mind, it's not just bare carbon, it's hot dip galvanized as well.
Yeah, I think that covers it. And then another question that we had from Lafarge was, what is the max depth of ferro masonry ties? And he was asking if there's a capacity for thicknesses of insulation in the 8 to 10 inch range.
So I know, Michael, we've done masonry ties up to 18 inches. I know we're working on a project currently that's up to be closer to 20 inches or even 23 inches. Michael, the second part is there a capacity for thickness of insulation?
Yeah, so we do also do, we provide our in-house testing for ties that are beyond, I believe it's 6 or 8 inches, so that we can work with the engineer to provide those custom products.
Yeah, and so just to add that, Alan, you know, one of the things that here in North America is that the BIA specifies any tie that's greater than 6 inches has to be engineered. So at that point in time, you would be looking for manufacturers such as ourselves to provide you an engineering report for a masonry tie that's has a thickness greater than 8 inches, 6 inches, sorry.
Great, and then I think that's it for any unanswered questions at the moment, at least.
Great. Well,
fantastic.
Thank you.
So I would like to thank you both, Adam and Michael, for the presentation. It was very interesting. I think thermal bridging is certainly a hot button issue here in New York, and it's a complex part of the building. So it's good to have a very detailed presentation by you guys, and good to see that there are good products on the market which we can use as architects and specify. So thanks for the presentation, and we will send out that recording and also the contact info of Adam and Michael, and everyone can continue asking questions, more detailed questions if you like. So thanks, guys.
Bye, everybody. Now, thank you for your time, and you can find us at ferocorp.com or you can find us at LinkedIn Fero Corporation. Thank you, and look forward to speaking with you. Take care now. Bye-bye.